Welcome to lecture 33. We'll be discussing another application of calculus variations. This time we'll be applying the buckling. I would like you to pause the video and look this YouTube video out. I'll also put in a link description, but I think it's a great video to watch um, for this application. What is buckling? Buckling is a structural failure due to excessive displacements. It's a loss of structural stiffness due to imposed loads. Buckling process is a structure that's subjected to loads, and the structures cannot withstand loads with the original geometry. So you started with the original geometry, you apply loads, and it cannot take those loads, but it doesn't fail. The structure doesn't fail due to material failure. Rather, it basically the structure changes shape to a new equilibrium configuration. It loses the stiffness. It loses the ability to contain those loads and sustain them. A possible outcomes that you may see when buckling occurs is structure displaces considerably. For example, when you take a can of Coke and it's empty and you step on it, you will see that with sufficient amount of force, the Coke can will buckle. And so the structure obviously displaces quite a bit. Large deflections may induce plasticity or failure, and structure may or may not fail catastrophically. What is a definition of stability? Changing the geometry of a structure or structural component under compression, resulting in loss of ability to resist loading, is defined as instability. So again, the ability to resist that loading we define as instability. Instability is a catastrophic failure mode, but you could also have stability. Every structure is in equilibrium, static or dynamically. If it is not in equilibrium, the body will be in motion. Stability qualifies the state of equilibrium of a structure, whether it's stable or unstable. So let's look at these three pictures on the right to kind of go a little bit deeper into the stability definition. On the right-hand side, I have a stable equilibrium. What is stable equilibrium? Stable equilibrium is when you apply small perturbations. Say you apply a little bit of perturbations to this little ball in this curve, on this surface that's curved. And so when I apply small perturbations, it does not cause large movements. The structure vibrates until it comes back to the equilibrium position. So this structure is considered stable. Structure is unstable, for example, in this case, when I apply small perturbations, and you can see that this ball will go off and roll. It produces large deformations, and the structure never returns to the original equilibrium position. A structure is in neutral equilibrium, and that means it may not be either stable or unstable, because when you apply small perturbations, it could cause large movements, but the structure you can bring it back to the original position with almost no work. Definition of stability does not always involve the geometry of the structure under compression. Buckling phenomenon that occur for structures under compressive loads can be stable or unstable. So if you have a buckling event, the buckling could behave in a stable manner or it could behave in an unstable manner. I'll be talking about that coming up so you can get a better understanding of what that is. Here are three pictures of buckling. Here you can see a hurricane near where I grew up. It impacted this tank. The winds buckled that cylinder. And in this case, you can see that the wall has significantly deformed. In this case, you also see a launch vehicle that buckled due to winds, and here you can see a launch vehicle buckled due to winds. Buckling is one of those phenomena that really need to be validated for launch vehicle designs, aircraft designs, and so forth. It is a very important consideration in aerospace designs, but it occurs in biology. The cicadas are very interesting insects. They will usually come out in prime number years, which is quite incredible to know that this is occurring in their genetics. And this is done so that it limits the number of predators that go after them. If you have even number years or years with large common denominators, common factors, then you're going to have more potential for predatory behavior. But by having particular prime number years where cicadas come out, then it's more unpredictable for predators to go after that. But what is incredible about this is that buckling, they buckle their ribs. They'll buckle their ribs at high speeds. And they do this to then make the noise that you hear cicadas make. And that noise is really done to attract other, uh, for mating purposes. It's a call for mating. And what is incredible is that they're buckling and then they'll mate and die right after mating. So, very interesting phenomena. They don't want to be eaten, so they come out prime number years. They buckle their ribs, which sounds painful, but perhaps it's not for them. And they're vibrating their ribs like a musical instrument, really back and forth, vibrating the ribs. And I really recommend that you look at the literature. You can study them more. It's a very interesting behavior. And then that's attracting it's attracting other insects, which then when they mate, they die right after that. So very, very interesting behavior. But buckling does occur in those insects. And you also have buckling here of our aircraft. The shear panel here has buckled quite a bit in an aircraft. And shear buckling is a fairly significant phenomena. You can see that also in aircraft design where you have these fuel barrier webs. These fuel barrier webs also could experience buckling and need to be designed against that failure mode. So let's look at stable versus unstable buckling because I discussed it in this configuration of a ball on a surface that's curved, but I think there's some value in really understanding what it looks like in a structure. So here on the left-hand side, I've applied a load. I've applied a load into this structure, and it's an axial load, a load P, and say that the critical load at which this beam will buckle is P critical. So say that's the critical load at which buckling could occur. And what does buckling mean? We already talked about loss of stiffness. It also basically could lead either to excessive deformation or not so much. When you remove the loads, maybe it returns. But if you take a ruler at home and apply an axial load in compression, when you apply a load, usually that ruler should bend quite a bit quickly. And the critical load for a ruler tends to be very small. But the bottom line here is that if you apply small amount of loads in axial compression to the ruler will stay straight. There's no deformation that will occur out of plane. So if I assume the outer plane deformation is delta, then I can look here, I apply a load P, you can see here, and there's no outer plane deformation. It's staying in compression and there's no transverse deflection delta. But when P equals P critical, you can get a small amount of buckling behavior, meaning you start to get a loss of stiffness. Here you can see that instead of going straight up, which that's a possibility, and that's these are mode of behavior that could occur is for it to go straight all the way up with no transverse deflection delta. There is a potential that if the load capacity increases after buckling, then you'll get a stable bifurcation. Why it's called bifurcation? Because I have a particular deformation here, which is straight, but then can then shift to different deformation. In this case, is bending. And that occurs right at that point. If I continue to apply a load, P above P critical, you can see that now it starts to go out of plane, and you can see here that I'm basically tracking this curve. So with applied load, increased load, delta increases. And you can see here that'll be a stable buckling configuration because when I release the load, it can come back to the equilibrium state, which was the original undeformed shape. Now, that's obviously true if there's no yielding or something like that. Once you get yielding, then that's a different story. But we're talking about pure buckling here. If the load capacity, if the load capacity decreases after buckling, so after this point it decreases, then it will be an unstable bifurcation point. The structure stiffness decreases as the loads are increased. So the structure stiffness is decreasing as the loads are increased. The structure stiffness decreases to zero and can become negative. We'll talk about that later. But when I look at the slope of P versus delta, that's still positive, meaning there'll always be some resistance. If you apply that load axially to the ruler, that ruler will continue to require more and more load, and it's going to be harder to bend them more and more. And you can see that's what's occurring with this curve. More load P, and I have a transverse deflection. That's exactly what you see in a ruler. So again, stable versus unstable buckling, the scenario is unstable is that I'll require less load and it just goes and continues to buckle very easily. Here's a situation where you can see here is buckling. I now take this scenario. I'll take this scenario and I'll make things worse by applying a bending load as well. And I'll apply a bending load to make it even buckle much easier. If I do that and I plot M here, you can see that it starts with stiffness K, and then it starts to buckle. So you get the delta there. And then once you get to this point, you get negative stiffness. That's unstable buckling in this scenario. So that does occur, and there are scenarios that can occur. So here I have another example. I have here stable region. So I'm applying a load P to this arch. And when I apply that, I'm in this region, P versus delta, P versus U. Here, P is a load applied, U is where I'm measuring that. You can see here that when I apply a load P is stable, I get to a particular point at which you start getting a potential buckling behavior. And it goes unstable. You can see here snap through. So you can see that this snaps through and it's very difficult to bring that back. So this region here is unstable. And then when I apply a load here, it's in a stable region because I'll be in this slope here. So again, buckling can be stable or unstable, and these examples are examining those different scenarios, so you can kind of learn more. Here I have a unstable buckling from a very close friend of mine, somebody I really appreciate very much. His name is Dr. Gustavo Cortez, and his research was on the loading application of plates with slits. And you can see here that when you look at the buckling behavior, that you can see here that for a perfect for a perfect structure, that you follow this straight line up, and then if I go unstable, I'll follow the dashed line down. So that's a negative stiffness with P delta. P is the load applied, delta is the transverse deflection, or the end shortening. Delta in this case is the end shortening. And what that means is how much it is contracted. You can see here clearly that this is a negative stiffness. When I apply a load P, if I go beyond this point, which I cannot go beyond, but when I reach this point, the structure will buckle and I need less and less load to shorten that column or this plate. For imperfect structure, you're going to be following more like this line here, and the more imperfect the structure is, you will have more of a slope, but you will continue to converge to this curve right here. A similar behavior happens with cylinder. You get an unstable behavior with cylinders when you apply a load and you look at the end shortening. Again, you get a deflection that's stable. So the load deflection is stable, and then you will get unstable behavior after it buckles, like a can of Coke under loading conditions. Let me define again a few terminologies that are quite important. You have the bifurcation approach, which consists of writing equations of equilibrium and solving them to determine the onset of buckling. You have the energy approach. So here in the bifurcation, so there's three methods, okay? That's what I'm trying to cover here, is the three methods for analyzing the stability of structures. The three methods are bifurcation approach, energy approach, dynamic approach. The first approach, the bifurcation approach, consists of writing the equation of equilibrium and solving them to determine the onset of buckling. That's all you can do with the bifurcation approach. The energy approach consists of writing the equations and expressing the complete potential energy of the system. So you take the equation and write the whole potential energy of the system. We will analyze this total potential energy to establish equilibrium and examine the stability of the equilibrium state. So the energy approach can help you with that. The dynamic approach consists of writing the equation of dynamic equilibrium. You will solve the equation to determine the natural frequency of the system, and instability usually corresponds to the reduction of omega to zero. So again, you apply loads to a structure, you calculate the natural frequency. What happens is, if you take this ruler example, and I were to compress it more and more and more, and I calculated omega, the eigenfrequencies, after I apply this compression load, you're going to see that omega is going to start dropping towards zero. And when it crosses zero, it is very known that that's the point at which buckling will occur, that load. So that's a very interesting approach, the dynamic approach. In this course, we're going to be looking at bifurcation approach and the energy approach, because the energy approach is very nice because you can examine the stability of the equilibrium state, something that may not be possible with the bifurcation approach. The bifurcation approach is appropriate for determining the critical buckling loads for a perfect system subject to loads. In the bifurcation approach, we're looking at deformations that are usually small. The system must not have any imperfections, and it cannot provide any information regarding the post-buckling load deformation path. I'll show you that through an example. But again, bifurcation approach is appropriate for determining the critical loads, buckling loads for a perfect system subject to loads. The deformations are usually small, and the system must not have any imperfections. It cannot provide any information regarding the post-buckling load deformation path. Want to make sure that's clear because we'll be looking at that very soon. And so again, what is buckling? Buckling, I want to make sure that's clear. Buckling is structural failure due to excessive deformations, loss of structure stiffness due to imposed loads. And again, a can of Coke that's empty and you apply a load is a perfect example of that. The energy approach is best when establishing the equilibrium equation and we can examine that stability. We want to understand if it's unstable, stable. The deformations can be small or large. The system can have imperfections. It provides information regarding the post-buckling behavior if large deformations are assumed. And the major limitation is that it requires assumption of the deformation state. That is the main thing there that needs to be examined. A major limitation of this approach is that it requires assumption of the deformation state. I'll be illustrating these two techniques coming up, and I think we will learn a lot when we do it. Let's look at this example, okay? Let's examine this example. This is stability analysis. And what I encourage you to do as I work through these examples, I want you to pause the video and kind of rederive this by hand, and that you take your time to make sure you understand what is going on as you're analyzing it by hand. What I want to do is examine this very interesting problem. This problem is a rigid bar. So this bar has no potential for deformation by itself. And I'm going to apply a load P. And this rigid bar here is actually constrained as a pin. And there's a torsional spring here on the left-hand side. And here, that torsional spring has a stiffness K, and theta is the angle of deformation of this rigid bar. Because it's a rigid bar, all it can do is rotate about that pin. That's all it can do. But this torsional spring, what it does, it resists that motion. Okay, so that's what we're going to look at. And what I want to do first is to write the equilibrium equation of static equilibrium in the deformed state. What that means is I'm going to take this load P, which is axial, and I'm going to assume that it buckled a little bit. And then I'll apply a load P in the same way I had it here. And you can see that the height here is L sine theta because this is theta and the length of the bar is L. This height is L sine theta. This is L cosine theta. This distance here from this pin all the way here is L cosine theta. But if this moves up, then that distance to the left is L times 1 minus cosine theta. So that's what we have so far. We will write the equilibrium equation in the deformed state. And so I'll take moments about M. So I'll take moments about M here, about this point here, and I get minus K theta, which is the restoring moment due to the torsional spring stiffness, plus P times L sine theta, because that's that height here that you see. That's how much it moved And so I have this P L sine theta, that's the distance that I have. And so that's the moment that I'm going to have in this situation. So P, this load P times this distance gives me the moment that reacts this restorative moment K theta. So that's the only equation I have. I can solve for P, and P equals K theta divided by L sine theta. For small deformations, sine theta is close to theta. So if I do that, then I get simply that P critical equals K over L. That's very interesting. This structure here, we know that it's going to buckle as long as the stiffness K is equal to the length L, which is extremely interesting question, situation here. The structure will be in static equilibrium in the deformed state when P equals P critical. When P equals P critical, we have buckling and the static equilibrium has occurred in the deformed state, and that's P equals K over L. When P is less than P critical, the structure will not be in the deformed state. Okay, so when P is less than P critical, it should stay straight. That's what we're saying, it's blue. When P reaches the value of P critical, that's in static equilibrium in the deformed state, and we get that P equals K over L. The structure will buckle into the deformed state when P reaches the value that's the critical value of K over L. So you can see here, it's very interesting how buckling only depends on the geometry and material parameters. Here, P critical only depends on the length of that rigid bar, and K here is the stiffness of that torsional spring. That's extremely interesting that has occurred. Now let's look at the energy definitions. The first definition from the energy point of view, let's look at Lyapunov's first theorem. If the potential energy in the equilibrium state is not a minimum, and I'm going to repeat that again, if the potential energy in the equilibrium state is not a minimum, and if the absence of a minimum is caused by second order terms in the Taylor series expansion of the total potential energy, then the system is unstable. I'll repeat again, if the potential energy in equilibrium state is not a minimum, again, the potential energy is something that we talked about in this course quite a bit. And what it's saying is if the potential energy in equilibrium state is not a minimum, and if the absence of a minimum is caused by second order term in the Taylor series expansion of the total potential energy, then the system is a minimum. So if the absence of that minimum is caused by the second order term in Taylor series expansion, then the system is unstable. The second definition here is a conservative mechanical system is a configuration state is a configuration of stable state if and only if the value of the total potential energy is a relative minimum, otherwise it is unstable. Again, a conservative mechanical system is a configuration of stable state. It is going to be a stable state if and only if the value of the total potential energy is a relative minimum, otherwise it is unstable. Very important definition that is worthwhile really understanding and spending time with. So two definitions um, to look at for the energy point of view. So what is that we're talking about here? You can use the energy method for elastic system. So again, when you have conservative forces, you can use the energy method for an elastic system. And the total potential energy of the system pi depends on the work done, WE, and the strain energy stored in the system. We talked about this extensively. For the system to be in equilibrium, its potential energy pi must be stationary. For the system to be in equilibrium, the potential energy pi must be in equilibrium. We talked about it very much. We set the first derivative of pi. The first version of pi must be equal to 0. We talked about that extensively in this course, and we demonstrated that the first version of pi really renders the system in equilibrium. Higher order derivatives of the total potential energy are examined to determine the stability of the equilibrium state. Whether the equilibrium is stable or not, you can look at that second, the higher order derivatives. So let's look at the rigid bar supported by the rotational spring again. Here I have that bar that we talked about, that rigid bar, with the actual force P applied, with a pin and the torsional spring at the very end resisting that motion. So then I'll assume a deformed shape again, which was this. We showed this before already once. And again, I'm applying a load P and I'm looking at what's going on with the deformed state. And what I want to do is calculate the total potential energy for this system in the deformed state. And what I have here is pi equals U minus WE. U, which is a strain energy, since it's a rigid bar, all we have is strain energy of the torsional spring. That's the only thing we have here that needs to be considered. So then that's 1/2 k theta squared, because that's the energy of a spring. And then I have the energy due to the external load applied. So I have a load P here. Obviously, the load P moved from this point to that point axially. And so P times that deflection in this direction is L times 1 minus cosine theta. So that's what you see there. And I hope you can see that that's L times 1 minus cosine theta, because when the bar is straight, that's L, but when the bar moves up, this distance here is L minus cosine theta. So that small little sliver here is P times that little sliver, which is L times 1 minus cosine theta. So pi is 1/2 k theta squared minus PL 1 minus cosine theta. I can take the first version of pi and set that equal to 0. That's just taking the derivative of pi respect to theta, really, to set that equal to 0. And what you see here is that I have k theta minus PL sine theta when I take that derivative here. I invite you to take the first version of pi so you can see that's the case. The first version of pi is the derivative of pi respect to theta del theta, and that's equal to 0. And when you do that, you will see that this is what you get. Well, when I do this, I have the derivative of pi respect to theta equal to 0, and I get k theta minus PL sine theta. Obviously, that's what I get from here, this derivative. And then from here, sine theta is small, can be small, we can make it theta. And then I get P critical equals K over L. This is exactly what I got before with the equilibrium approach, the one here. We just did it here using the static equilibrium equations. And I got the same answer with the energy method. The energy method predicts that buckling will occur at the same load P critical as the bifurcation analysis method. We saw that. At P critical, the system will be in equilibrium in the deformed state. Let's examine the stability by considering further derivatives of the total potential energy. So we'll look at, we'll examine the derivatives of pi adjacent to theta equals 0. What I want to do is look at, okay, derivative of pi respect to theta is this, and here's k theta minus PL theta. I made that approximation. So I made that approximation there. So we're examining derivatives around theta equals 0, meaning I am close to this straight configuration. That's what we're doing there. And when I look at the derivative of pi respect to theta squared, that's k minus PL. Well, when P is less than P critical, obviously this will be greater than 0. So that's a stable equilibrium. When P is greater than P critical, I'm getting that this is less than 0, which is unstable equilibrium. And when I have P equals P critical, I get this equal to 0, so I'm onshore. So three outcomes from these analyses were found. Now, and when I look at this carefully and I map all this up in here so we can see what's going on, we say, okay, in state number 1 is stable when I'm in the straight line, so P is less than P critical. Obviously, this is greater than 0, so that's stable. And that means that this rigid bar is straight. It's straight as I'm applying the load P, and there's no out of plane deflection theta. So then I get to P critical, this value P critical, and we're saying it's unstable when P is greater than P critical, so it's unstable here. And we have no idea about the state during buckling. So we don't know what's going on here at this point. And the reason I don't know is because at P equals P critical, we're onshore. That's equal to 0. We have to examine maybe higher order derivatives. And we have no idea about the post-buckling equilibrium path. We don't know what's going to happen at this point, or whether it's stable or not. So we can do a large deflection analysis. Instead of assuming we go through the same process that I had before, but instead of assuming that theta is small, I'll leave it as is. And I'll say, well, I'll take the pi respect to theta, the first version of pi, set equal to 0, and I get k theta minus pl sine theta, and set equal to 0. And I can solve for p, and I get k theta divided by l minus sine theta. So the difference between this analysis here was I assumed small deflections, and I got rid of the sine theta, made it theta. So that made a small deflection right there, which made it equal to the bifurcation approach earlier. So once I get to this point, p equals k theta divided by L sine theta, I can now plot what is going on, So we can see here, we can look at the post-buckling behavior very clearly, and the load carrying capacity increases after buckling at P critical. So I can plot this now. Okay, so I get P equals K theta divided by L minus sine theta, L sine theta. And if I were to call K over L P critical, so I get P over P critical, and I call K over L P critical, then I have P over P critical equals theta divided by sine theta. Now we know that this point here corresponds to K over L. P critical equals K over L. We know that. We found that that's the case, and that's when buckling occurs. But to plot this, then all we have to do is P divided by P critical and plot it versus theta divided by sine theta, and then we can see how this curve behaves. And you can see here, this should be stable because when I apply a load beyond that, I can increase the load and with an increasing value of theta. So then the large deflection analysis can help us examine the stability much better. We did it here earlier, but it left us without some information. When we go to large deflection analysis, perhaps we can gain a better understanding. So when I look at the second there's the pi respect to theta, I get k minus pl cosine theta, and we know that the p equals k theta divided by L sine theta. So I can plug that in here at buckling, and then I get k times 1 minus theta divided by tangent theta. But for any value of theta, this is greater than 0, so you're always stable. This is always stable. And then when theta is 0, you get derivative pi with respect to theta squared is 0 for theta 0. So at that particular point is onshore. But at values larger than theta, you can see that's greater than 0 for sure. So I now know that it's stable here in this curve, is stable here in the straight line up, but at this particular point, I'm not sure what it is. We don't know what that is because due to pi respect to theta squared is 0 for theta equals 0. Um, and you know that when I put theta equals 0 here, I get k minus pl, but the critical value at buckling's uh, k over l, so this gives you 0. So you can see here that I'm kind of stuck. So then I have to examine higher order derivatives to figure out what is going on. When I do that, I can find the derivatives, second variation, third variation, fourth variation, and I'll set equal to 0 here. That's equal to 0 there. That's equal to 0 here. That's equal to 0 there. And then here is also equal to 0 at theta equals 0. So you're onshore again by looking at third variation. The fourth variation gives me a value now, and that's PL cosine theta. But P again is K over L, so I get uh, at theta equals 0, this is P times L, so I get only K. And and obviously, when I look at that fourth variation, I get 1 over 4 bang, there's the 4 pi respect to theta to the fourth, theta equals 0, and theta to the fourth. And this is clearly greater than 0. K is greater than 0, 124 is greater than 0, and theta to the fourth is greater than 0, close to theta. So therefore, uh, we have a stable state right at P times, we have a stable state right when buckling occurs. So that's what we've done, and so now I can show it here completely. This is stable. This point is stable and buckling occurs, and then I'm also stable in this whole regime. Meaning, what it means? It means going back to the definitions. When I remove the load P, I expect the rigid bar to return back to the original state, right? That's what stability really meant there. We know that bifurcations are over here because I went from one equilibrium state, which is the rigid bar straight, to a deformed rigid bar at the pin. It rotated about the pin, and but I know that's stable because when I apply a load, it can return back with back to the original state. So here you see how we've done it. And now we can look at new examples that we have the energy method here. We have a rigid, now we have a rigid bar that's pinned here, but we have a translational bar spring here at the end. That's the difference between the previous analysis and this one. We're putting a spring here versus a torsional spring there. And we're going to do the same approach. We're going to go to the energy method because you can see that the energy method provides a lot of good information where the bifurcation method doesn't. So we can look at the assumed deformed state. And here you can see that this is a deformed state of that particular rigid bar. And you can see I'm going to rotate on amount theta again. And so that spring gets stretched. Okay. And let's see what happens. Let's study this example. This height here is L sine theta again. So I can calculate the moment, but I will do the energy method instead. We know that this distance from this point to this point is L times 1 minus cosine theta. So very similar approach as we had before. We know that this stretch an amount KL sine theta. So from this point to this point, that's a stretch of that amount. And so we can look now at the energy. The total potential energy is that the energy of that spring is 1/2 K L sine theta squared. And for small amounts of theta, if it were to be small, then you have 1/2 KL squared theta squared. And then the external load causes a potential energy, and that's the load P. And how much travel distance that load moved, that will be P times that distance, L times 1 minus cosine theta. So a very simple calculation so far, nothing very fancy so far. Pi is 1/2 KL theta squared minus PL times 1 minus cosine theta. Here, we can see the derivative of pi respect to theta. The derivative of pi respect to theta gives me KL squared theta minus PL sine theta. So if I take that derivative, I get sine theta. So I get derivative of pi respect to theta is 0, KL squared theta minus PL sine theta. But sine theta could be small, could be theta, close to theta, for small theta. And so I get KL squared theta minus PL theta equals 0. And I can solve now for the critical buckling node P. And you can solve it here. You get actually a very similar answer, K over L. And so again, the energy method will have predicted the same critical buckling load as the bifurcation analysis method. I didn't do it here, but if you did it, you'll find that. At peak critical, the system will be in equilibrium in a deformed state. We're able to do so. We can examine now the stability by considering further derivatives of the total potential energy. I can look here, derivative of pi respect to theta is KL squared theta minus PL sine theta. The derivative of pi respect to theta squared is KL squared here minus PL cosine theta. And for small deflections, uh, theta equals 0, around theta equals 0, you get KL squared minus PL because when theta is small, cosine of 0 is 1, so that's what you get. And so this is telling us that when P is less than the critical value, KL, you can check it there, then this is in a stable configuration. When P is greater than KL, then you have an unstable configuration. And you can do that by checking this. If this is greater than 0, right, you can solve for P, and then that's what you get. When P equals KL, or when you set this equal to 0, you find that P is just KL, and you cannot tell what's going on. So I'm finding the stable here, unstable here, and unsure there. So what if I now kept I didn't make the small deformation assumptions. And so I kept sine theta there, cosine theta there, the whole thing there. So I don't make any small deformation assumptions. Then I get KL squared sine theta cosine theta minus PL sine theta equals 0. And I get that's equal to P equals KL cosine theta. So when I set the first version of pi equals 0, that's what I get for equilibrium. So again, P equals KL cosine theta for equilibrium. And again, when theta equals 0 is the bar is straight, and that's exactly when buckling is about to occur. You can see here that I can plot it again. I can do P divided by P critical, and you can see here P critical is what we talked about earlier, K times L. You can see here when I take this ratio and I plot it, I get this curve now, which is actually a cosine theta curve. And you can see here when I reach a critical value for buckling that theta goes unbounded by decreasing load P. So it takes no load. There's negative stiffness. So that's unstable because when I reach a critical value, any deviations from that causes the structure to go out of equilibrium. But I want to really look at the higher order derivatives, looking at large deformation analysis, not making those assumptions I made earlier where I met theta close to theta. I want to do it with a large deformation analysis because it gives me more information. So I will do that. I know pi is this, derivative of pi with respect to theta is this, derivative of pi with respect to theta squared is this. And for equilibrium, we know that P equals KL cosine theta. So you can plug that in here. And when I plug it in, I get that all this is minus KL squared sine squared theta. Well, this always less than 0, so it's an unstable configuration, period. I don't have to even look at third variation, fourth variation, and so forth. However, at theta equals 0, if you recall, at theta equals 0, I can't tell what's going on at this particular point. I don't know if it's stable or unstable. And as a consequence, I should examine higher order variations. We already told you that at, at, at this value here, theta equals 0, you can see theta equals 0 there. When I take the derivative of pi respect to theta, I get this. Second version, I get this. At theta equals 0, you can see that this is equal to 0. So I'm not able to say more. The third variation of pi also will give you 0 because sine of theta is 0. And so all this gives you 0. So I have to look at the fourth variation of pi. And when I look at that one, I'll get this expression and I'll be able to, at theta equals 0 then, I get minus 3KL squared. And that's clearly less than 0, which is unstable, clearly unstable at theta equals 0, and that's unstable at buckling. So that's what that's telling us. Since the first non-zero term is 0, the state is unstable at P equals P critical and theta equals 0. So therefore, it's unstable in this here, it's unstable there, and it's also unstable here. So actually stable in this straight line. I apologize. It's stable in that straight line. So that's a mistake. This should be stable here, but unstable are in this curve, unstable at that point. So I will then consider the bifurcation analysis again, and I want to look at the adjacent method really quick, which is what we've been using to some extent, and I want to show you another example. In this example, we'll consider two rigid bars connected to two torsional springs and is pinned here at this bottom point. So rigid bars again with a load applied P with a torsional spring here, a torsional spring there, and then we also have so let's look at this example again and let's calculate pi, the energy. Now what you have here is a torsional spring here, so it can rotate amount alpha, it can rotate amount beta there, and you have a load applied P here. And so what is the total energy is 1/2 K alpha squared here. And this moves on amount alpha and this moves on amount beta, then this torsional spring is only looking at alpha minus beta or beta minus alpha. So 1/2 K alpha minus beta squared, and then this P this load P moves an amount delta downwards, and that delta value can be calculated as L minus by geometry, just pure geometry. So if this rotates an amount alpha, then this point moves downwards an amount L times 1 minus cosine alpha, and then this point moves an amount downwards L1 minus cosine beta. So I can calculate that delta very easily. And now all I have to do is expand using Taylor series expansion about this state, this equilibrium state. So I have pi equals pi naught plus delta pi naught plus second version pi naught, etc. I'm just really deriving calculus versions again, but I can bring this to the left hand side. We've done this before, and this dominates the expansion. I set the equal to 0, and the system is in equilibrium only if this is equal to 0. So derivative pi respect to alpha del alpha plus derivative pi respect to beta del beta. Obviously, you have alpha and beta there, and that's equal to 0. So first version pi equals to 0, and I can now do the calculation. So the first version of that is can be found very easily. The derivative of pi respect to alpha, derivative of pi respect to alpha is this. Derivative of pi respect to beta is this. And I'm not making any small approximations right now. But you can see here that alpha equals 0, beta equals 0 is a trivial solution to the problem, meaning that the rigid bars will be straight when our load applied is P. It can happen. It could be straight. So alpha is 0, beta is 0 is a trivial solution. And is this configuration stable or not? And you look at the second variation of pi, and that must be greater than 0 for stability, right? And if it's 0 again, if this is 0 again, then you have to examine the third variation and so forth. So that's what we have so far. So stability verification is to examine the second variation to determine whether it's positive for stability. And so we can examine higher order variations even using this formula here. And for this problem, the second variation, you can do that second variation very easily. We've shown you how to do that. But the second variation using this formula is going to look like this. There's a pi respect to alpha squared, del alpha squared, and so forth. And we evaluate these at alpha equals 0, beta equals 0 to see what's going on. That's one approach. That's one approach that's typically used to determine the nature of the stability. So we're going to use the Tres criterion. What is a Tres criterion? The Tres criterion allows us to calculate the critical state based on a formula called the adjacent equilibrium method. That's the method I'm discussing now. It's called the adjacent method. And so what is that? So at the limit state of stability, the second variation ceases to be positive definite. So at the limit state of stability, the second variation ceases to be positive definite. And for this to occur, it requires that the first variation of the second variation must turn to 0. And so the condition for stability limit is this. So again, at the limit state of stability, the second variation ceases to be positive definite. Obviously, when the second variation becomes uh, not positive definite, that's when you have an issue with buckling. And for this to occur, it requires that the first variation and the second variation must turn to 0. And so the condition for stability occurs to determine the critical state. Tres criterion was developed in 1933, and I want to describe it a little bit different following here. So stability criterion reduces to the condition of the second variation uh, be positive definite. So sorry about that. So the stability criterion reduces to the condition of the second variation be positive definite. Therefore, when the critical load is reached, the second variation becomes positive semi-definite. That is, the minimum value of the second variation is 0, and this value is attained for some angles alpha and beta. Hence, the condition that the second variation poses a minimum of 0 for some non-trivial values of alpha and beta reduces to Tres criterion for arbitrary virtual angles del alpha, del beta. In other words, we have to take this first variation of the second variation of pi, and this is not the same as the third variation of pi, by the way. We're just trying to determine when the second variation of pi changes sign. And to do that, we find the first variation of the second variation of pi to determine when that happens, because we know that when the second variation of pi goes from positive to negative, that you must have a stability issue. And so that's why this is very powerful, this first variation of the second variation. That's really what we're trying to figure out. We're trying to figure out what values of alpha and beta this could happen. And there's a little trick that needs to be adopted here, because it can get very confusing to find the second version of pi. And I really encourage you to do this manner. So we will call del alpha equals alpha 1 and del alpha beta equals beta 1 for sanity purposes. Otherwise, things look very complex. And so I'll go back here to this formula that we're talking about, and I'm making this alpha 1, beta 1, alpha 1, and beta 1. We're doing that to make things a little bit easier for our eyes. And so, and then this whole thing we're gonna call Q. We're gonna call this whole thing Q. And then I'll take the first version of Q because that'll be easier to see with our eyes. Otherwise, if I look at this one, it looks very difficult to execute. But if I look at this, it's much easier. If I call this whole thing Q and find the first version of Q, and Q is second version of pi, this makes it much tractable for our eyes. So, so that's what we're gonna do. For our problem, the second version of pi is we had to find that derivative here. And when we do it, we get 2c minus pl. This derivative here gets c minus pl. This one gives you minus 2c. And so that's 1 over 2. And now I find the first version of q relative to the alpha 1 and beta 1. And that's easy to do. This has to be equal to 0. That has to be equal to 0 based on the stress criterion. That's what I get. Again, I'm evaluating this equal at alpha equals 0 and beta equals 0. That's what I'm doing. And that's why I get these expressions. And I think you should pause the video and see if you can get the same answer I got. But these are the equations I need to solve now. And the trivial solution is alpha 1, beta 1 equals 0. And the other solution is for this determinant to be equal to 0. And when I do that, I can find the determinant, and I find the loads, the critical loads at which buckling could occur. And I find these values, but I also find the eigenmodes, the values of alpha and beta that will give you this exactly to 0. You get two eigenmodes, and it's interesting that one of the eigenmodes looks like this, the other eigenmode looks like this. And I'll let you decide which of these is more critical. Obviously, 3 minus square root of 5 divided by 2 is more critical, while 3 plus square root of 5 divided by 2 is more difficult to attain. The lowest critical value is the one that should happen. And there's an eigenmode that I want you to see if you can figure it out. There's one eigenmode that's more critical. Why don't pause the video and figure it out and post it in the comment box for extra points. But we're able to find a critical value of buckling using the stress criterion. And to start over, or kind of like summarize, we use the adjacent method here. You draw the system in equilibrium in the buckled state, and you calculate pi. It's basically the energy method. Then you find the first version of pi, and when you do that, you're able to find that alpha equals 0, beta equals 0 is a trivial solution. That's all you get for that. But the question is, if this is equal to 0, this term is 0, what can help us determine stability? And so we examine the second version of pi, and the second version of pi can be looked at, and we use stress criterion, which says find the first version of the second version of pi, and that's called the adjacent method, really. And I taught you a trick on how to do that. I call del alpha alpha 1 to make it easier for our eyes to kind of calculate everything. And then the first version of Q is the first version of the second version of pi, and this is what you get. For our problem, we calculate the second version of pi very easily with alpha equals 0, beta equals 0. And then del Q is equal to this times del beta 1, this times del alpha 1. And then we can proceed forward. And then we saw that alpha 1, beta 1 is a trivial solution for the second version of the first variation of the second version of pi. But we found that the determinant is another possibility, and from there we found the critical value by looking at at, the solution to this characteristic equation. So we get two eigenvalues, two eigenmodes, and one of them is the most critical. Great. So we made a lot of progress here in determining what how to calculate buckling. So while we don't look here at order buckling calculations, let's look at this order Bernoulli beam under compression load. You have a load applied P here, and the beam should stay straight if the loads are small and there's no imperfection. The total potential energy for this beam is the integral from 0 to L 1 half EI W double prime squared dx minus P U times L, because that's the strain energy and that's the potential energy. We've done that several times now. Now we want to consider something called the von Karman approximation for moderate rotations, large deflections. I already covered this in a previous video lecture, but let me remind you. So the strain was calculated as derivative of u respect to x plus 1 half derivative of w respect to x squared minus z times the curvature. That's what we got. We usually have been dropping this term. When you're really working with buckling, you want to keep nonlinear terms. And you know that when things buckle, um, then it's very unlikely that the neutral axis will change in distance. So as a consequence, we can look at setting this term, the neutral axis strain, we can set that equal to 0 when buckling occurs, because it's unlikely that that neutral surface will change in value. It does make sense when you're applying a compression load that a neutral axis is compressing, but once it buckles, you'll expect things to come back to 0. So if we set that equal to 0, then I can write derivative of u respect to x equals to the minus 1 half derivative of w respect to x squared. I'm going to do a little trick that is going to involve something very quick here. So let's do a trick, and I'll get back on what that trick is doing. But say I have this p times derivative of u respect to x. So dx. So I'll integrate by parts. And if I integrate by parts, I get p times u of L minus u of naught. But the deflection at this left-hand side is 0. So that's p times u L. And what I'm saying here then is that derivative of u respect to x, based on this, is 1 half derivative of w respect to x squared. That's what I found. And so I can say that this left-hand side is equal to this right-hand side, and there's a negative sign there. And that's pu of L. So I can then take this p times u of L at the right-hand side and convert it into what's in there. So it was a little trick to get everything into something. So we took the actual load and converted it somehow into a slope term. That's very powerful. It's a trick that was used back in the day. And that trick was helpful for trying to determine when buckling occurs. One more time, the total potential energy is clearly that, no questions. The strain is this, derivative of u respect to x plus, and then we allowed a nonlinear term here. And we assume the neutral axis is inextensible during buckling, meaning that neutral axis is not moving. It's not going to change in shape, or sorry, it's not going to stretch. So we made that equal to 0 and solve for du dx. And then I used a trick here to show you that p du dx is the same thing as p of u of L by integration by parts. And that this is equal to the minus 1 half that, because du dx is that. So if we substitute that, we get this, and then we can, uh, so we get the first and second variations by expanding using Taylor series expansion. We already done this before. I can use epsilon eta, like Taylor series expansion, but I'm going to do it this way. It's fine. W plus del W squared minus W del W. I could have put here epsilon eta as well in here. But this is the way I'm doing it, which is fine. And then when I expand this, I get this is pi, this del pi, and this del squared pi. This one gives you equilibrium, so we set that equal to 0. So you have gotten the same answer if you took this first version of pi here. The second version of pi will give you this. If you did it, that's what you will get. And we already know how to get the second version of pi. And now what I want to do is find the first variation of the second version of pi. That's what I want to do. So I'll call this W1 and double prime and W1 prime. So I've done that, W prime, double prime, and W1 prime. And I call the whole thing Q. So I'm calling this whole thing Q. Okay? So I call that Q. And the first variation of the second version of pi, then it's easier to see because it's the first variation of Q, really. And when I do that, I find this calculation. And then we integrate our parts. And when I do that, I find that I set this equal to 0, and then I integrate our parts to find that this here is the order Lagrange equation, and I have the boundary conditions associated with that. So that's the governing equation establishing bifurcation, and the boundary conditions are driven by these terms that came from the integration of our parts. And if I were to apply a particular situation, so I were to find a beam that's clamped here with a rotor here on the right hand side. The governing equation for that is EIW4 primes plus PW prime equals 0. We found that through here, the order Lagrange equation. The boundary conditions for this problem is clearly clamped here, and then also it is allowed to rotate here, so that's 0. And so now I have the general solution to this problem, and the general solution is this, if I want to solve it exactly. And you can go ahead and impose these boundary conditions to get the characteristic equation, which is going to give you the critical buckling load of 20.16 EI divided by L squared. That's when buckling occurs. I apply a load P, and that's when buckling occurs. You've seen this before in mechanics of materials, but you probably didn't know where this equation came from. Now you know. It came from Euler Lagrange equation and by the Treft's criterion. You can see here that I get 20.16 EI L squared divided by L squared. And notice how the critical value of a buckling occurs. And that's the exciting part about buckling, right? It depends only on the material property, the cross section, and the length. The longer the length, the easier to buckle it. The greater the moment of inertia, the harder to buckle it. The greater the modulus, the harder to buckle it. So very interesting here. We're able to find the buckling load. But what if I want to use the Ritz method? So we can approximate, instead of trying to solve it, right, in an exact manner, we can use Ritz method. So we can assume an approximation of A1 x squared plus A2 x cubed. So it satisfies the clamp condition on the left-hand side. It satisfies W0 equals 0 for essential boundary conditions. W prime of 0 equals 0. And so that's a good polynomial approximation. The second variation is this. We already saw that. We'll plug that in here. And when I plug it in there, now Q becomes a function of A1 and A2. So all I have to do is find the first version of Q, which now depends on A1 and A2 alone. And when I do that, I get this equation. So that's as simple as two systems of equations times A1, A2 equals 0, 0. You can see here that I'll get two equations, one from here and one from there. And so that's the first equation, and that's the second equation. So I find the determinant, and the characteristic equation gives me 2.486 for the first buckling load. The second buckling load is 32.2. For the first buckling load, the error to the exact solution that we just got is about 0.75%. So I can use Ritz method as well to calculate the buckling load in a very, very simple way. So what about buckling of plates? So this is like a buckling of plates. So the total potential energy of a plate under in-plane compression loads and shear loads using Kirchhoff theory, and we already covered Kirchhoff theory. If you're to calculate the strain energy of a plate, this is what you will get. this right here. The mechanical work of the applied forces, in a very similar manner, I showed you how this load P, how this load P here becomes an internal work like that, P W prime squared. In a very similar manner, you can show that those external loads applied become these terms right here. You can see that they're P times W prime squared. That's what we had before. I apologize. I moved the slide too quickly. You can see that it's kind of there, but now you have other loads applied in other in-plane directions, NX, NY, and NXY. And so this is your total potential energy. And if you were to find the second variation of total potential energy, and I encourage you to do it, this is what you will get. You'll get W1. This should be W1. I apologize. So all that is W1. Um, and you will get basically this expression. Then we can use, for simply supported plate, I can show you that this expression here satisfies the essential boundary conditions of the problem. And the good news is I can plug that in here to calculate buckling. For uniaxial compression loading, only keeping NYY and NXY to 0. So just to make it simple, we'll just drop this term and this term to make everything simpler. You'll find that this is the characteristic equation you will get. And these signs can go away to 0. So the only thing that we need to do is solve for n. And when you do that, you get n bar equals d. And d here is the property of that plate, modulus t cubed 12 1 minus nu squared. So this is what you get. And buckling occurs for the smallest possible value of the load. That's when buckling occurs. Therefore, n equals 1. Has to be 1 there for, for buckling to occur. And the buckling coefficient is usually written, you can rewrite this expression as n bar c equals kc pi squared d divided by b squared. All you have to do is extract out b squared. And when you do that, you get a buckling coefficient. We call this the buckling coefficient. This expression here, I recommend you pause the video, but you will see that when you multiply this by that, that is going to be the same as what I have here. It's the same thing. I just set n equals 1 because that's when buckling occurs. And so it just makes it very easy to show it in this manner. So my next step now is to determine when buckling really occurs because I still don't know. So so again, this is the same thing as that. And I want to point out again, we found the second variation, right? And we are using the risk approximation. So we plug that in here. And when we did that, we find the characteristic equation, which is this. And then n bar, the buckling load nxx can be found. And then we wrote this in a different way, just because buckling occurs when you have the smallest value of the load, and that occurs when n is 1. But now you have this expression that needs to be looked at. Well, what you can do now is you can plot the buckling coefficient. You can plot this buckling coefficient here. Notice how uh, pi is known, d is known, the width of that plate b is known. So case is the only thing we need to figure out how to minimize. And so you can see here that for various values of a over b, I can plot that. And so here for m equals 1, I can put m equals 1 here and determine for a particular value of a over b, I'm sorry, for a particular value of a over b, you can then determine what m should be used to minimize the buckling coefficient. So that's how that works. You can see here for a over b, for example, of over here, say, of squared over 6, you can get this value here. M is the number of waves that's going to form due to the buckling. N equals 1 is basically how many waves in the other direction. But that's how you calculate the buckling coefficient is using this graph for a particular A over B. Say I have 5, then that corresponds to M over 5, and then I can get the buckling value. You can actually get the buckling coefficient for other types of boundary conditions. The one I showed here is for simply supported, but there's other ones like free, uh, free, simply supported, clamped. So you can actually basically determine the buckling coefficient for other kinds of situations that may arise. And these are the cases A, B, C, D, and you can go here and look at what case you're looking at for your situation. I encourage you to look at these articles, pause the video, and download them. This is the original articles by von Karman. And I feel like you will understand everything here because you learned so much so far. But here you're looking at the buckling of thin cylindrical shells under axial compression. And I covered plates, but here you can see how you will deal with um, cylindrical shells. And you can see strains and stresses are being calculated. You can calculate the energy due to applied loads. And so this paper goes through the exact same things we've been talking about. And you can even see here the little trick for the integral that we did earlier here is I know it's small font. You can download this paper from your library. So the Journal of Aeronautical Sciences, 1941, Volume 8, number 8. And when you go through this paper, you'll see that they find the buckling coefficient, just like we were plotting them before for plate, but for cylinder. Very nice that we can show uh, that we're able to get very similar things. Here you can see that for cylindrical shells, the behavior is unstable. So when you increase the load, you can see how the load has to decrease for it to buckle. So you have a negative stiffness behavior. And the paper goes through a lot of information about testing of buckling, and they showed that uh, actually in this paper they show how the buckling predicted by classical theory tends to be smaller than what you will get from testing. And the reason is because you have imperfections in cylinders that could become a problem. I have a whole video on buckling that goes through that. I encourage you to look at that. Is under the advanced aerospace structure class. I have the video there. With that said, I want to thank you for uh, going through this with me. I also encourage you to buy this book called The Buckling of Bars, Plates, and Shells by Dr. Professor Robert Jones. It's a great book. It goes through the very similar things I discussed today. And I really hope you found this very enjoyable. Buckling is a very enjoyable topic because um, it really is. It's you don't have to do an experiment to determine when buckling occurs. It just depends on the geometry and material properties. And then for shells, it also depends on the imperfection measurements. With that said, I thank you very much. I hope you learned something today. You look at my videos on buckling of a more practical approach to really going about this in my advanced aerospace structures course. With that said, have a great day.